My name's William. I'm here from Sandia National Labs, and I'll be presenting on various biological dynamics that enable training in binary recurrent neural networks. The overall inspiration for this work and the target sort of goal is to be able to embed neural networks into analog processing arrays for remote sensing applications. So here in the top left is an example of some previous work from my co-authors, where they have a series of images that are coming in one by one on some sort of dark background. And at some point in time, there's a bright yellow dot that comes on. And we're essentially just trying to classify these images one by one and determine when this event occurs. You can imagine doing this with just a convolutional neural network and trying to treat each of the images individually. Or you can try to do the same sort of spatial processing with convolutional nets, followed by a recurrent neural net that's going to incorporate how those features have changed over time and possibly give you some sort of additional fidelity in detecting those events. And indeed, they find that when you add the convolutional front end with the recurrent back end, you're able to increase the precision of such a network for detecting these simple events. And this is nice because it means you have these sort of feed-forward convolutional layers early in the network. And these are easy to embed into analog memoristic crossbar arrays. So here we have inputs coming in on each of these rows that are going to go, this is input voltages, either from the camera or earlier layers of the network. And then the weights of the network are going to be applied just by current laws through these programmable resistors. And then on the bottom of each of these columns, we're going to be accumulating current, which will be sort of the activity from this layer of network. And then that current needs to be integrated over time and transformed through an analog to digital converter into an activation function. This, because the vast majority of this network is analog, it's mostly passive. The majority of the power consumption is going to be occurring in this analog to digital converter at the bottom of the network. So what we would like to be able to do is to find a way to train a network to be amenable to a lower bit activation. For instance, if we start with an 8-bit activation function, we get about 80 operations per watt, whereas if we can move this to a binary activation function, we get about 50 times the number of operations with the same amount of power. So what we'd like to do now is find a way to bring recurrent neural networks into the same sort of analog approach. To do that, I introduce a new task, which is going to be what I call the small object tracking. So we start with just static images from the DIOR dataset and introduce various aspects to it to create a synthetic video. So we begin to move the camera around. We introduce noise on individual pixels that evolves through time. And we introduce a small single pixel object that's going to have low luminescence compared to the overall background. An example video is here, where you can sort of see that the camera is slowly moving over the scene, and there's sort of white noise on the individual pixels. And actually, there's an object here now outlined in red that's very difficult for us to see. So this is a very difficult task, primarily because the signal noise ratio is so low. You can look at individual frames from this video down here to sort of see that the intensity of the object is actually just sort of washed out by the natural variation in the scene. To start to think about how we could process a stimulus like this, I have a simplified version here that focuses in on a just 30 by 30 cutout of that larger image. And I've changed the way that the noise evolves so that you can see this individual object just sort of moving around frame to frame. But again, if you just look while it's still, it's mathematically impossible to detect the object. What we can do in certain cases is some sort of temporal preprocessing. So because of the way the noise has been generated in this task, on the right here, I'm just going to play the temporal difference frame to frame. And it's very easy to locate where that object is, right? So there's this pattern where there's going to be a white dot and a black dot indicating that neighboring pixels have changed in a predictable manner. So that sort of temporal preprocessing works only in the case where I've adjusted the noise of the background image to be slowly varying so that the temporal difference is extremely clear. If we go back to the original scenario where I had that full field and the individual pixels have sort of pop-like noise, applying that sort of front pre-processing doesn't allow us to easily extract the position of the object. So here in the in the blue, I have just a convolutional network trying to process those individual frames as a function of training, and the individual pixel mark is here, and noise is essentially at the top of this axis. So while the network does learn to sort of predict what quadrant of the visual field the object is in at any point in time, it doesn't actually locate the object. And in orange is that same sort of pre-processing where we just apply the temporal difference. And again, because the statistics of the noise have changed, we're no longer able to sort of predefine what operations need to be done to extract that information. So we need to find a way to allow the network to extract these fine-scaled temporal kernels that might allow us to detect minute changes in local intensity of objects. So what we want to do is move away from the CNN-RNN, or spatial bin temporal approach, and move to an approach where we have convolution and recurrence at every layer of the network. An individual layer here is called a convolutional recurrent layer, and we essentially have two different pathways for information to be integrated. The top is just your traditional sort of feed-forward convolutional network trying to extract spatial features. And the bottom is going to be taking the activity of every unit at every point in time and sort of propagating it through an additional cross-channel convolutional bank. So we have the ability to sort of detect objects as best as we can, as well as try to learn filters that are going to be able to extract those local changes in intensity. Those are going to be summed up and passed into what is essentially a local state, similar to the membrane potential of a neuron. And those are going to persist locally through time and go through some sort of activation function. In this case, the hyperbolic tangent that goes forward into the network and also through those convolutional recurrent connections. When we introduce these convolutional recurrent layers, we now have these chain curves down here that are all performing sub-pixel localization. So with these low signal noise ratio and even tracking, even though the object is sort of detecting, occupying a pixel, we're able to sub-localize within the pixel based on where the object was on previous frames. Mm-hmm. And in this red box are various cases where I've changed slightly the number of recurrent layers, and essentially they're all able to perform essentially the same just as well, as long as we have one convolutional recurrent layer at the beginning of the network. So we have to have this recurrence very early in the processing stream. Otherwise, if we try to put it later, we have this brown curve up here, where essentially spatial processing before temporal processing has caused us to lose the ability to detect the object as accurately. This is problematic because we, again, are trying to embed this into an analog array with low binary activation. And recurrent layers have a tendency to be very difficult to train with binary activation functions. So if I take that same topology, the convolutional recurrent networks, and replace the activation function with binary activations, the heaviside activation function here, the training is now back up here in that sort of baseline performance where we're just detecting which quadrant of the image the object is in. When we are training these types of networks, what we do is we have, during the forward pass, activity is propagating through the network according to this solid red line here, the sine function. And during the back propagation phase, we are assuming that instead of this true activation, we had a sort of surrogate approximation of that. And as long as the network activity is able to stay in this -1 to 1 range, where the two functions are changing with respect to each other reasonably, these approximations can be valid and we can back propagate through time or in linear layers. As soon as we introduce a recurrent layer, though, the network sort of ping-pongs itself between activating with units activating or shutting themselves off. And so as we try to perform back propagation through time, the network spends very little time in this sort of valid approximation region. In contrast, there's been a lot of work, including people obviously at this conference, who have worked with spiking neural networks trained with surrogate gradient descent. And what's interesting is that if we take that same activation function, so a leaky integrated fire neuron, and introduce it into this topology, this green line now is the training with that spiking neural network. So the spiking neural networks are able to be trained in this recurrent topology. What's interesting is that both of these are binary activation functions. In one case, we have the sine activation, and the other we have a single spike, but both of those are 0 or 1. And in both cases, we're using a surrogate gradient to try to approximate how weights should be updated in the network. So the question next is essentially, what is the difference between the heaviside activation function and the LIF that enables this difference in training? So there's a number of sort of modular changes that can be made to take us continuously from the binary activation network to the LIF. To address this, we designed what we're calling the generalized leaky integrated fire, where we have a block diagram of this sort of the individual units now here on the left. And I've outlined in these dashed lines essentially different modules that we can take or remove to slowly transition us from the heaviside activation to the generalized LIF. So we have inputs coming in on the left. Those are integrated through time into membrane potential changes, which may or may not leak. In all cases here, I'm going to be using just a binary activation when the neuron reaches threshold, which is going to elicit spikes that could travel up the network. When the unit reaches that activation, typically a spiking unit will have an explicit reset function, but this is, again, something we can take out to see how necessary it is for the network. We also introduce a hyperpolarization, which can be thought of as a sort of soft shutoff mechanism. So here in the bottom right, just to illustrate a couple of those combinations, the sort of temporal response to step functions, as we add or subtract these modules, we get different dynamics out of the individual units. So we can take all the different combinations of these possible sub dynamics and run them in, again, that recurrent convolutional network and perform training. So here in this table, I have the second row right here is sort of the baseline, the hyperbolic tangent RCNN, has an MSE of about 0.007. And then after that, I have sort of decreasing complexity, starting with the full model with the hyperpolarization, leak, explicit reset, and sort of decreasing the complexity as we go down in this table. So we see that the first several entries in this table all have errors that are within 2 to 3 times the baseline performance of the hyperbolic tangent activation function, indicating that adding or subtracting these different dynamics doesn't drastically affect the performance of our network. The only ones that are significantly different are these bottom 2 entries that I've highlighted in red, and both of these leave out the integration term. So as long as we have the integration of inputs into membrane voltage, we can take or leave explicit resets or leaks or hyperpolarization. If you think about it in a bit more depth, this makes sense because what the integrative term is doing is sort of smoothing out our membrane potential through time. And that membrane potential is what we're doing the surrogate gradient descent on. And so by having this low-pass filter, we sort of stabilize the temporal dynamics and avoid that situation where units are going to be switching back and forth between on and off very quickly. We can also, in order to verify that this sort of result of needing the leaky integrator is not just a byproduct of the task that we designed, we next test on 2 additional tasks. So we have here on the left, the free spoken digits data set, which is just a sound file of people speaking the digits 0 to 10, 0 to 9. And we've decomposed it into a spectral component such that each column here, an example outlined in white, is what we're going to be providing our network at each point in time. And so this is a primarily temporal task. The network is going to have to detect changes in the relative frequencies to classify the spoken digit. And then in the bottom right, we have the MNIST data set, which is just a spatial labeling task. So we have a temporal, a spatial, and a spatiotemporal task that we're comparing these different subunits of those. Here is the same sort of tables I showed before. On the left is the MNIST, and we see that all variations of the generalized leaky integrated fire are able to train, again, to more or less 98% accuracy. Indicating that in the case of the sort of atemporal task, it's not incredibly necessary for the network to have this integrative term. However, for both the temporal FSDD task and the spatiotemporal task, we find that, again, these bottom 2 rows have a much lower accuracy. So when we have a temporal or spatiotemporal task, it's absolutely essential for the units to have, at the bare minimum, just that integrative membrane potential. So far, this is all focused on sort of what the only requirement is, which is that integration term. One very large difference What's interesting here is that we have something like the integrated fire model and also a non-spiking binary leaky integrator perform essentially the same task with the same accuracy. If we look at the learned recurrent weights for these two different types of units, on the left I have the LIF recurrent weights, and on the right the binary leaky integrators. And I want to emphasize here in this black box the sort of self connections in these networks. So on the left for the LIFs, in the middle of each of these 3x3 grids, there's this, in every single one of these, there is this strong self-excitation. So what this means is that even though there's an explicit reset built into the LIF units, once one of the neurons activates, it's actually going to try to elicit a spike from itself on the next time step. The end result is that on average, a neuron after it fires, rather than resetting to membrane potential 0, will be at about 0.2 on a 0 to 1 scale. So it's already 20% of the way to firing again. If we look at the binary leaky integrators, which lack that explicit reset, we see the opposite trend. So again, each and every one of these recurrent weights has a self-inhibitory term. So even though we no longer have that explicit reset, the units, once they come on, are going to strongly inhibit themselves, such that, again, their membrane potential is going to be about 0.2. So they are learning a soft reset mechanism. The end result is that for these two different unit types, in both cases, we have a firing rate, if you will, in the case of the LIS, or an overall activation in the case of the BLIs, with about 10% of the units active on every time step. This is nice because it means, depending on the constraints of our hardware, it may be easier or harder to implement explicit spiking. And if it's difficult in the case of various hardware, we can actually just rely on the network to learn the self-inhibitory term instead. Right, so all of this so far has been sort of on simulation or numerical algorithm development. But again, the end goal was to bring this into analog hardware. So what we've done next is we can take those spiking neural networks that have been trained and deploy them into CrossSim, which is our software of choice for simulating sort of the physical noise of the analog crossbars, including things like read and write error, parasitic currents, digitization of weights, all sorts of things that come along with this noisy analog setup. If you just take essentially any network that's been trained without these various sources of noise and deploy it into simulations of the hardware, you get drastic increases in decreases in performance. So what we've done is we've, as of last week, there is a public beta available of CrossSim that we have essentially implemented surrogate gradient descent the same way that we did for the spiking units. Now we have built-in surrogate gradient descent for analog noise. So during the forward pass, we're going to actually run a full simulation of the physical hardware, including things like here, write errors in our analog array. And those errors are going to propagate all the way through the network during the forward phase. During the backward pass, we are going to assume instead that instead of having this full physical simulation, each layer did exactly what we wanted it to. So we're going to assume the analog writes were completely fine, that parasitic currents don't exist, and so forth. And so by doing what we call the analog in the loop training, the network is actually able to find ways around a lot of these different sources of noise, such that for the FSDT task and the small object tracking, at the end of training in the loop, we get minimal decrease in performance for the analog simulation compared to just a floating point implementation. And so in addition to simulating just sort of the analog crossbar array itself, we can also explicitly put in the hardware mechanisms that would be necessary for either the leaky integrate and fire or the binary leaky integrators. And so now here in this image, we've replaced the ADC with just an op amp and a capacitor, showing how we might actually implement these different unit types. And so again, I've done end-to-end, taken those same networks with the same units and put them into this analog simulation with minimal loss in performance. And for anyone that's interested, on Friday, I'll be working through a tutorial session, basically showing how you can take those exact networks that I showed earlier and run them in CrossSim. And so this is a way to do sort of analog in the loop training of spiking neural networks. All right, so summary points. First is that I show that for this low signal noise ratio task, you need true spatiotemporal processing in order to extract local changes in pixel intensity. While binary activation units are not able to train in that setup, LIF units are. And the only sort of dynamics you actually need out of those LIFs are the integration term of the inputs to the membrane potential. I want to emphasize here that what we've done is essentially look at a very specific type of task we wanted to do, right? We essentially have a machine learning task that we want to train LIF units or integrative units to perform. And we've been able to strip away the vast majority of the complexity of a true neuron and even of a leaking a grain fire. That's not to say, in the spirit of the talks from earlier, it's not to say that there's nothing else the units are doing. As a neuroscientist, I want to emphasize this is sort of the bare minimum that a neuron has to do for this type of task. Additional temporal dynamics are certainly necessary for mechanisms like learning or multiplexing of information. And then again, finally, we can take these networks and implement them with analog in the loop training and get true analog spiking neural networks. It's like that.